Rotational kinematics is a natural extension to the linear kinematics, what we've been studying so far. To start off with our study of rotational kinematics, we first need to talk about rotational measurements, or several of the quantities that we'll be dealing with as we solve rotational problems. First, we'll start out with something's angular position. And the angular position is defined as being the symbol theta, and it's an object's linear position divided by its radius. The units for an object's angular position are radians, or at least those are our standard units, but you may also see units of revolutions, and in which case 1 revolution is equal to 2 pi radians. Another quantity we'll commonly use is something's angular displacement, or delta theta. Just as linear displacement, angular displacement is a change in something's angular position. So theta 2 minus theta 1, or theta final minus theta initial. Again, since we're simply subtracting, the units are radians. After displacement, the next logical quantity is velocity. And velocity, angular velocity, similar to linear velocity, can be found using a derivative, d theta dt, or the rate at which an object's angular position changes. Now, this gives us an instantaneous angular velocity, but if we would just want an average value for something that's traveling at a constant angular velocity, we could use the angular displacement divided by time. In either case, the units are radians per second. Those are our standard units, but quite often you'll see things measured in revolutions per minute, and in that case, you'll want to convert to radians per second. And lastly, we have angular acceleration. And similar to linear acceleration, angular acceleration is the rate of change of the angular velocity with respect to time. Once again, this is an instantaneous angular acceleration. If we simply wanted an average angular acceleration, we could do the change in angular velocity divided by the change in time. Units here are radians per second squared. Just a couple quick comments. The biggest comment being that for now, as we start off this study of rotational kinematics, we'll assume that our object is a rigid body with a fixed axis of rotation. So it's rotating about the same spot, and our object is not changing in its shape in any way, shape, or form. We will learn how to deal with what happens if the shape or the distance from the axis of rotation changes further on in our study of rotational kinematics. But let's continue on in the simpler version. Now, we know that linear displacement, linear velocity, and linear acceleration all have direction that can be indicated using words or angles or symbols or unit vectors. Similarly, our angular quantities have direction. In the past, you may have talked about that direction as using clockwise or counterclockwise. And while it makes sense that an object can rotate clockwise or counterclockwise, that's actually not the true direction of angular quantities. Instead, angular quantities have a direction just like linear quantities do that can be represented as the x, y, or z direction, positive or negative, and can also be represented using I hat, j hat, and k hat. To find this direction, we have to use a new right-hand rule. This right-hand rule is a little bit different than one that we've learned in the past. And to help us understand it, I have a little image here. So if we have an object rotating, similar to this disc that you see rotating here, we're going to use our right hand and curl our fingers the direction of that motion. So curling your 4 fingers around, it's basically almost like you're making a fist here. Curl your fingers around the direction it rotates. Point your thumb straight up. That thumb indicates the direction of your angular quantity. So for example, here we see that this top disc is rotating counterclockwise. And so when we rotate our hand around it, we see that our thumb points upward. So the direction of this angular velocity would be in the positive y direction. Similarly, if we rotate clockwise now, we have to turn our hand upside down to rotate our fingers in that direction. And so your thumb's pointing downward, indicating that it's in the negative y direction. You can also do this with your thumb pointing in the positive or negative x directions, or positive or negative z directions, or any angle in between those. Remember that the direction of angular velocity is the same as the direction of angular displacement. And to determine the direction of angular acceleration, you want to think about whether the object is speeding up or slowing down, and therefore whether the angular acceleration is the same direction or the opposite direction of your angular velocity. Now, when we have a constant angular acceleration, there's a few other equations that we can calculate, or that we can use to calculate quantities in rotational kinematics. Two of these equations are found on your equation sheet. The first of those equations being the fact that the final angular velocity is equal to the initial velocity plus acceleration times time. While we commonly do not put vector symbols on top of these quantities, it's important to remember that they are vectors, and you do need to pay attention to the direction. Another equation that's on your equation sheet is the equation that the angular displacement is equal to the initial angular velocity times time plus 1/2 angular displacement times time squared. By the way, remember that this funny looking W here really stands for omega. It's the Greek letter omega. And my symbol here is a Greek letter alpha. So alpha represents angular acceleration, omega is angular velocity. Now these two equations are the ones that are on your equation sheet, but there really are two others that can be used. We have that the final angular velocity is the initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. And while this equation isn't on your equation sheet, the linear version is. The one that says VF squared equals VI squared plus 2A delta X. Since the linear equation is on your equation sheet, it's totally fine to use this equation without doing any sort of derivation. Lastly, we have an equation that says the angular displacement is 1/2 the initial angular velocity plus the final angular velocity times time. Now this equation doesn't appear in any format on your equation sheet, and the reason it doesn't is this is just basically one way of saying that the average angular speed is the angular displacement divided by time. Because this average angular speed is equal to 1/2 of the addition of the initial and final angular speeds, as long as your acceleration is constant. And notice that, as we talked at the beginning of this slide, these equations work only when your angular acceleration is constant. So all four of these equations are on your equation sheet in one format or another. One last thing to learn about when it comes to rotational kinematics, and that's the idea that there is a relationship between linear and angular quantities. So we already stated that the angular position is equal to kind of a location of your object divided by the radius. Radius in this case, remember, is the distance to the axis of rotation. So if I reformat this equation, I get that my linear position is my angular position times my radius. Now remember, I can take the derivative of both sides of this equation. ds dt is equal to d theta dt times r. R is a constant in this case because we're assuming that our object is rigid and remains the same distance away from the axis of rotation. ds dt is otherwise known as velocity, linear velocity to be specific, and d theta dt is otherwise known as angular velocity. So the linear velocity is equal to the angular velocity times the radius, or the distance to the axis of rotation. Similarly, I could take the derivative of both sides once again. And I would find that the linear acceleration is equal to the angular acceleration times the radius. So in each case, there's a relationship between the linear version and the angular version of this quantity. Just a side note, this velocity equation is the only one that appears on your equation sheet. So that means that you need to be able to justify the other equations, namely this acceleration equation, before you use it. For this equation, the position being the angular position times the radius, that's a definition, and therefore you are welcome to use that equation without having to justify it. In class, we'll do plenty of example problems using these concepts to make sure that you're comfortable with angular kinematics before we move on.